Hello, I'm Myungguen Choi from Hokkaido University, Japan. The script of this talk will be read by Google Cloud Text-to-Speech.
In the field of human-computer interaction, the exploration of novel input methods using head-mounted displays in the domains of virtual reality and mixed reality is an active area of research. The eye-gaze interface is one of the promising input methods because it is fast and the eye tracker can be naturally mounted onto the head-mounted display. However, the eye-gaze interface has a problem called the Midas touch problem that the target at the user's gaze is selected against the user's intention. One of the factors causing Midas touch is false selection due to short dwell time. Another factor causing Midas touch is false selection during visual search. Visual search is the action of finding a particular object among other objects. Visual search causes gazing beyond the dwell time, resulting in object false selection. Complex visual search increases the required dwell time. Zhang et al. Confirmed an error rate of 16.9% when the dwell time was 1.1 seconds in a visual search task where labels were present in targets. Pfuffer et al. Confirmed an error rate of 9.7% when the dwell time was 1.0 seconds for a shopping task. One of the reasons for the high error rate in the visual search task was that the labels were written inside the target. Penkar et al. Found that separating the target from the label reduced the Midas touch rate of the task, even at short dwell times. However, target and label separation has been studied in graphical user interfaces in a 2D display environment, and not in 3D virtual reality environments. We aim to separate the eye-gaze interaction area and visual search area in the VR environment. In a natural gaze shift, the difference in the direction of the gaze relative to the frontal direction of the head rarely exceeds 25 degrees. However, the maximum physical range of human eye movement is about 45 degrees. The user's gaze goes at the 25 degrees to 45 degrees angle region infrequently. In other words, gaze interaction at this angle is unlikely to cause the Midas touch problem. In this work, we present a Kuiper Belt, a menu selection method to solve the Midas touch problem by placing the selectable menu items within the 25 degrees to 45 degrees angle region. We conduct two studies to explore the design principle of how to place menu items in the out-of-natural angle region named Kuiper Belt. We investigated the characteristics and limitations of the eye-gaze interaction in the Kuiper Belt with study number 1. There were two independent variables: eye distance and eye direction. Result of study number 1 showed the larger the eye distance, the worse indicator of error rate, physical comfort, and mental comfort worsened. In addition, the top right, and top left indicators were lower than those in the other directions. Next, beginning with the smallest eye distance, 5.2 degrees, 7.8 degrees, 11.7 degrees, 12 degrees, and 16.3 degrees were found to be the appropriate menu item sizes. As a result, it is recommended to place menu items at eye distance equals 32 degrees for upward directions and at eye distance equals 37 degrees for other directions. In addition, the recommended menu item size is about 12 degrees. In study number 2, we investigate whether the Kuiper Belt method is an effective method to solve the Midas touch problem. The task in study number 2 is a visual search task to find and select a correct panel in 16 panels and then select a color of the panel from menu items. The corrected panel is the panel with a unique symbol. The corrected color is the correct panel's color. For this time, we compare three interfaces: 2SS, HG, and KB. The 2SS is the baseline for the gaze-based menu selection method. First, the user selects a panel by looking at the panel. After the user selects the panel, the user selects an item in the menu by looking at the item. This is a view of the 2SS at each dwell time. HG involves the simultaneous application of target selection and menu item selection. First, the user turns their head toward the target. Next, the user selects an item in the menu by looking at the item, while the user's head pointing at the target. This is a view of the HG at each dwell time. Target selection method for KB is the same as the HG method. The location of the menu items to be placed and the menu region are different between HG and KB methods. This is a view of the KB at each dwell time. Result of study number 2 showed when the dwell time was 200 milliseconds, KB reduced the error rate by 89% compared to 2SS and by 68% compared to HG. In addition, when the dwell time is 200 milliseconds or 400 milliseconds, KB has less Midas touch than HG. KB had significantly better SUS scores and all NASA TLX scores than 2SS. KB had significantly better mental, temporal, and performance of the NASA TLX item than HG. KB was the most preferred method with a dwell time of 200 milliseconds. Participants preferred KB, HG, and 2SS in that order. The average ranks for KB, HG, 2SS were 1.44, 2.00, 2.44. Here, we show 4 example applications utilizing our findings from the user study. First, we developed a menu item selection interface. The menu items are placed outside of the FOV while users are looking toward the front to avoid interfering with their views. Once the user's gaze enters the Kuiper belt, the menu items move smoothly into the Kuiper belt. The second example is a remote for controlling home appliances in VR. This remote is used similarly to the KB. The user first selects a target appliance with the head direction and then selects menu items displayed around the FOV. As a prototype, we implemented a TV and lamp operation. The third example demonstrates selecting a small and dense object from a group of objects. When a user looks at a group of objects, which has a target object to be selected, each object will be highlighted with colors. The selection is then completed by selecting a menu item placed in the Kuiper belt that has the same color as the target object. The fourth example demonstrates that the user can select an item in a game with the eye gaze interface. We developed an application that instantly changes items by selecting a menu icon placed on the Kuiper belt. This application allows for fast, no-handed item changes, and no Midas touch during vision search.